So, let us start with say P and R, let us say P and R. See, all the premises are given to us and we want to conclude this. So, you can at a time say that all of them are given, therefore, I can AND them together, right. So, let us say all of them are ANDed. Q. So, this is the proposition we get by taking conjunct of all the premises. Okay. Now, I can apply some associativity rule or commutativity rule, because we want to see that Q and S are together. So, how can I get Q and S together? I have to move out all the other things, right. So, use commutativity and associativity. So, once you have associativity, this parenthesis can move anywhere. Once you have commutativity, their order can change, right. So, we can just comment out that we have using commutativity and associativity. So, by using this I can write as P and R and T as 1 and the other as S and Q, or if you take commutativity you can write also Q and S, right. So, let us write that. Fine, but we do not want only this, we want only Q and S, not all the other things, right. So, what would give us that? The law of elimination, which says x and y, from there you can conclude x, from x and y you can conclude y, right. So, that is called law of elimination. Using that we can go for this entails Q and S. Okay. So, just look at what we are doing here. In the first instance we are telling this is equivalent to this, okay, because the laws of commutativity and associativity, they give us equivalences, x and y and z is equivalent to x and y and z. Also we have commutativity in the form x and y equivalent to y and x, that is a law, but in that law we first consider x and y or z even as propositional variables, then those propositional variables have been substituted here, right. So, you are using uniform substitution, is that okay. So, for example, here when you come from commutativity associativity, we take P and R and T first we take. So, associativity is used, commutativity is also used, both the things used simultaneously with uniform substitution, right. Then from this step to this step again the same procedure, x and y entails y. So, x and y are considered as propositional variables, there you substitute x as this, y as this, then you obtain this. So, see that all the laws and the meta theorems are in work. Okay. So, these laws, these meta theorems like uniform substitution, we are not mentioning it anywhere, because of those only we are able to apply the laws. Okay. So, we will not mention them even, since they are, it is permitted, so we proceed, that is the way it will proceed. Then such a thing is called a calculation. So, a calculation would look like some proposition you will start with, then you join with the next proposition by one of these two symbols, equivalence or entailment, okay. And each of those sentences together, some equivalence or some consequence relation, they are justified by the use of laws and the meta theorems, fine. But finally what do you get? You would be getting first sentence or first proposition entails or equivalent to the last proposition, okay. If at least once you have used entailment, then it will be written as entails. If nowhere you have written entails, then it will be equivalent also, because equivalence is stronger than the entailment. You know that x is equivalent to y if and only if x entails y and also y entails x, right. So, that is stronger. Therefore, at least once occurrence of entailment will produce only entailment at the final result, right. So, now let us see the second one. P implies Q implies R, not R, P entails not Q. So, how do you proceed? P so that is by modus ponens, right. P implies Q implies R. So, this gives modus ponens Q implies R. Now, Q implies R not R gives not Q by modus tollens, its name is modus tollens, right. So, you can write a calculation. So, we start with P implies Q implies R. Now, if there are many premises, so you may not like to add them all together at the beginning. What we do is, as we go along, whenever we need a premise, we just add it together. Then in that case, on the documentation line, we will be writing P, that is something else we are introducing here, which is a premise, right. So, for example, here we can start with one P itself, because we need it from the beginning itself, right. So, now our plan is to use modus ponens here. So, we just write document it as modus ponens, which entails Q implies R, right. Then what happens? With Q implies R, we want to add also not R, fine. So, here itself you can add not R, or from here you can plan what is happening, right. So, in that case you say this and not R. So, here first thing is you are using a premise, right. Next thing is you are using modus tollens to conclude the next sentence. So, you write modus tollens and this entails not Q, that is the end of it. Modus tollens says x implies y, then not y, this entails not x. Okay. This is not difficult to see. See, by contraposition, x implies y is equivalent to not y implies not x. Now, use modus ponens. So, it is a combination of modus ponens and contraposition. Okay. Let us see the third one. P implies R implies not P implies not Q implies Q implies R. So, how do you propose to go about? This should be valid, right. That is what we want to prove. It looks a bit clumsy, because from P implies R you are getting all those things. But anyway, if you start thinking that way, then you can use deduction theorem, right. So, by deduction theorem you can start from this, prove the whole thing after the implication sign. Again that is an implication sign. So, you can again take this as assumption, try to prove this, that is also in the form of implication. So, you can take Q again as a premise, prove only R, right, it is a serial implication. So, that means by deduction theorem we need to show that P implies R, then not P implies not Q, Q entails R. Is it clear? There are 3 steps. First step is P implies R, this entailment goes here, replaces the implication sign, right. P implies R entails this whole thing. Next step is again that is in the implication form, conclusion. So, you say P implies R, comma, not P implies not Q, entails Q implies R. Next step again bring Q to the left side. So, you obtain this. Now, can we show this? It should be easy. Yes.
Q implies Q implies R, so Q and Q is there.
Yeah. So, suppose you want to use modus tollens, then this should be in the form not Q, which is because Q is equivalent to not Q by double negation, right. So, you can start from there. So, let me start with say Q and I intend to use double negation. Okay. So, that is equivalent to not Q and I introduce another premise. So, and not P implies not Q. So, justification is adding a premise and then for the next step I want to use modus tollens. So, let me write modus tollens. So, that gives entailment. What does it give? Not P. Negation of that, right. Look at modus tollens, it says x implies y not y entails not x, right. So, this is your x not P, y is not Q. So, not y, x implies y, that gives not x. So, not P, okay. Is that right? Then you use double negation again, that gives P and add the other premise. So, you have used another premise here and plan is to use modus ponens. So, that gives Q R. Clear? But even you can prove this directly. Let us have another calculation. We have not used equivalent substitution till now. See, the problem is you have used modus tollens and double negation to bring to one form where not symbol is not there, right. Now, not P implies not Q, yes, can be replaced by Q implies P because of contraposition, okay. So, let us try that avenue. So, we can start the calculation from P implies R as is given, not P implies not Q implies Q implies R. Our aim is to use contraposition here. So, you write contraposition, that makes it equivalent to P implies R implies Q implies P implies Q implies R. Next, distribution of implication, right. So, distribution of implication says this is equivalent to x implies y implies x implies z. Now, it is matching with the right side. So, that we can replace by the left side. So, that says equivalent to P implies R implies Q implies P implies R. Okay. Is that right? Then this is your distribution of implication that we have used. So, let us mention it here, distribution of implication. Next, what to do? Our aim is to show that it is valid. Well, this itself is valid. It is your hypothesis invariance. X implies y implies x, right. So, you say that x implies y implies x is valid itself. So, that means it is equivalent to top, that is your hypothesis invariance, fine. So, you want to apply that. Now, with x you have P implies R here, and with y you have Q here. Okay. So, we just write hypothesis invariance, and that is equivalent to top. So, in a calculation when you want to show something valid, it will be easier to show that that is equivalent to top, because you are going through equivalences or entailment, or you can show top entails that. That may need some ingenuity, which one to introduce you would not know. Top is a constant, it can be written in any form which is valid. So, which form will give rise to that one will be a bit difficult to find out, right. But this way if you go end with top, it might become easier. Is it clear? P implies Q implies R. Next premise is S implies not P. Next premise is not S and T implies Q. We want to show that this entails T implies R. Any doubt? So, take a little bit of time to see how to form the strategy. So, first thing you should see is the conclusion is in the form T implies R. Okay. It is an implication. So, you can use deduction theorem, fine. So, by deduction theorem we show P implies Q implies R, S implies not P, not S and T implies Q, T entails R. So, it needs some back thinking, some backward thinking will be required here. How to get this R? We have here P implies Q implies R. So, you must show first P implies Q. In order that you will be able to apply modus ponens, right. Now, how to get P implies Q? Q will be obtained from this, right. So, not S and T should be proved. Okay. Then not S and T, where from? From P you can get not S, T is already there. Is that okay? So, you need P and then you will get not S, then not S and T will give you Q, therefore, you have P implies Q, where from you get P implies Q, you are getting only Q, but you are getting Q from the assumption that P. Is that okay? So, you have got really P implies Q by deduction theorem. So, it looks the strategy should work. Do you understand the backward reasoning? It says we want R, so you should prove first P implies Q. Now, to prove P implies Q, we assume P, derive Q. So, if you assume P, then along with this it gives not S, right. You have not S, you have T. So, from that you get Q, therefore, P implies Q. Is that okay? Then from P implies Q, you go to R. Now, where to start? How to start it? T? Because the problem is, if you prepare the way we have prepared here for the deduction theorem, at a time you have prepared this and then it proceeds, but here there is a problem. If you prepare like this, it comes only to this, and in between you have a sub lemma that is to be proved, P implies Q. Now, to prove P implies Q, you have to assume P and then come to Q in a deduction theorem, right. So, that becomes a sub calculation inside the calculation, that is creating problem. How to adjust the sub calculation inside a calculation? Well, you can have something like indentation, follow on indentation, prove it, then come back by the deduction theorem, but that will be looking clumsy. Well, here only reduction or absurdum will help. So, what do we do? Take negation of R with this, try to prove bottom, fine. So, let us try that. By reductio ad absurdum, we show P implies Q implies R, S implies not P, not S and T implies Q, T not R, and tells bottom. It should be unsatisfiable. Okay. So, now you have another premise which is not R, you can use it here, then modus tollens and continue. Strategy clear now? So, let us start with not R, which is a premise, and then add also P implies Q implies R. Okay. In the first step, you need not write premises, because anyway you have to start with premises. Okay. So, two premises we have taken. Our plan is to use modus tollens, not y, x implies y gives not of x, fine. So, let us write modus tollens which gives entails negation of P implies Q. But how to use negation of P implies Q here? You have to use it some of its equivalent form, right. So, its equivalence is P and not Q, right. Negation of P implies Q is P and not Q. So, that is called as implication, right. You can say implication. So, law of implication that gives equivalent to P and not Q. Now, then we have to introduce some more premises. Which one we will take? Either this or this, because Q is there, P is also here. So, one of these you can use. Which one? Choose. Which one will use? This or this? is non deterministic, you have to choose something, then start with this one, S implies not P. Okay. So, and S implies not P. So, we are using a premise here, and then what else? P is modus tollens, you want to use modus tollens because S implies not P is here. So, first you have to bring it to not Y form, right. So, double negation, that is equivalent to not P with another not Q, and S implies not P. Then you go for modus tollens. Modus tollens is not an equivalence, right. So, this entails with this is your not Y, this is X implies Y. So, that gives not X, not S and not Q. Not S is here, T is also here. So, you can use a premise T, this is a premise, but not only that, you need not S and T implies Q also. So, let us use that another premise. Okay. Is that clear? But then we want not S and T together. So, you need associativity and commutativity of and, fine. So, let us write that. For this, bringing them together. So, this is equivalent to, okay, we can keep it, we do not know whether we will need it or not. Let us continue and see. So, not Q and not S and T and not S and T implies Q, right. So, next we want to use modus ponens X and X implies Y, there should be a bracket here because of precedence rules. So, then we have modus ponens which entails not Q as it is and Q. Now, you see it is coming of help. So, this is the law of constants that gives bottom. In fact, it is equivalent to bottom. Is it clear? So, the question is whether X entails bottom, X equivalent to bottom, are they same or not? No? Answer should be yes, because bottom entails anything trivially, right. So, when we say X equivalent to bottom, it means X entails bottom and bottom entails X, but bottom always entails X, right. So, therefore, they are same, X entails bottom or X is equivalent to bottom. Is it correct? So, we need only bottom here anyway, it entails is enough for us, but you can write also equivalent here. Finally, anyway it is entails bottom, because there is at least one entail symbol here. Okay. Since it is implication, we can simply start with P and R as a new premise, and your conclusion will be this one only, right. So, by deduction theorem, it is enough to do this entailment, right. So, when you are making the strategy, you look at the conclusion, it is in the form of not W implies V. So, there is one way, not of W implies V is equivalent to W and not V, right. So, from all these premises you can infer W, you can also infer not V, then AND them together and conclude this, that is all right. Or there is another way, you can use reduction of Absurdum. So, that W implies V once taken as a premise will give you bottom, that looks easier here, right. You do not have to do so many calculations. Okay. Let us take that view. So, we add W implies V as a premise and try for reaching bottom. Okay. So, just one application of deduction theorem, one application of reduction ad absurdum. Now, we can think where to go. See, all these are implications except one, which is P and R, from which you can use P, you can use R also. So, let us take P. If I take P, I would get not Q, not Q would give me T, right, T would give not V, okay. Let it be there, not V, you can take not W also, but does not matter, stop at not V even. So, from P I can get not V. What can I get from R? R gives S, S gives not U gives W, W gives V. So, V not V will give bottom. Is it clear? So, let us start. We start with P and R. So, this entails P, but our strategy says we want to use also R, right. So, let us keep R throughout, right, that will also be helpful, we will not eliminate now. So, then from P I want to use P implies not Q, right. So, I can just keep R as it is and then manipulate all the others, fine. So, instead of entails P I will introduce a new premise P implies not Q and keep my R as it is. Okay. So, let us start with this AND P implies not Q, this I can start with. So, I want to use modus ponens. So, that gives R is kept as it is and P implies not Q gives not Q. So, it is not only modus ponens, I have used commutativity, R comes beginning, associativity I have not used a parenthesis anywhere, and is there, right. So, both the things are used implicitly here, associativity and commutativity, fine. Now, with not Q our plan is to use not T implies Q. So, introduce another premise here. So, I have used a premise and then we want to use modus tollens. So, that gives R and not of not T, right. So, at a stage if you want you can put double negation here, okay. So, not of not T will be equivalent to T now, fine. With T, which one? This one, modus ponens. Had this not T been on the other side I could have used modus tollens, right, but it is on the left side. So, I can't use that, but this one I can use by modus ponens. So, I introduce another premise T implies not of V. So, premise and modus ponens, that gives R and not V. So, our plan was to keep not V there, start expanding from R, right. So, then for that we need another premise which is R implies S. So, we will use P and then R implies S will give by modus ponens not V. So, let us give not V here and R implies S will give us S, fine. Then our plan was to use S implies not U, add a premise and then use modus ponens to get not V and not U. So, our plan was to use not U implies W. So, we add a premise and use modus ponens that gives not V and W. Okay. Next step, W implies V. So, add a premise and use modus ponens. So, that gives not V and V. There we are done. So, it is the law of constants. Intel's button. Is that clear? Okay. See, we had observed some discomfort in one of the problems, where we had to use reduction ad absurdum because deduction theorem becomes a sublemma, and our proposal was you can have some indentation, so that it is a sub calculation inside a calculation, then conclude and carry on, right. But to do that sublemma inside, sub calculation inside a calculation, you have to write a line by deduction theorem and so on, because we are not able to use deduction theorem as it is inside a calculation. Okay. The sequence of steps which are joined by equivalence symbol or entailment symbol prevents us to do that, right. So, the proposal is, what do? We forget equivalence, we just continue with entailment and do not write it, right, because everything is entailment. So, we will not write it at all, but then how to use deduction theorem, for example. So, we can evolve some schemes. For example, suppose I have x, I have y. So, this I am taking as an extra premise, and I see that by entailment relation all these entailments gives me y. Then I conclude in the next step x implies y, but when I conclude this x implies y, here this extra assumption is removed, it is no more an extra assumption. Without assuming anything, I could have concluded x implies y by deduction theorem. That is the way deduction theorem should work, right. Assume some extra premise and then conclude y, then finally you say without assuming that extra premise I could have got x implies y, right, because deduction theorem says sigma union x, x is an added premise, entails y, therefore sigma entails x implies y, fine. So, these things can be incorporated provided you do not have a calculation like this, but just continue the proof thinking that everything is an entailment, right. So, what we do there is we have to mention this, that it is an extra premise, and then mention it here that my extra premise is removed, it is no more an extra premise. So, these two things we have to tell in some way, right, we have to write it in some way. So, what we do is, when we take this extra premise, we will write deduction theorem begins, right. So, here we are using the deduction theorem starting, then when we end it we will write deduction theorem ends. Okay. So, it will tell us that inside this we have used deduction theorem with this as the extra premise, then have concluded this by taking away that extra premise, right. Similarly, for reduction ad absurdum, what we do? You are taking another assumption, say not w, sigma union not w entails bottom, right, therefore sigma entails w, fine. So, we can add one extra premise not w, which is an extra premise, then finally with entailments we get bottom, and the next step should be w without this extra premise anywhere. By assuming this extra premise, whatever sigma is used, those premises from sigma can be used here also inside this, but then after this once we derive bottom we say that this extra premise is now removed to say that all the other premises used entails W, that is what reductio ad absurdum is, right. So again here what we do, we will just mark it with reductio ad absurdum begins, and then when we conclude this W after the bottom we will write reductio ad absurdum ends, right. So we are just thinking it loudly, how to implement it we will see, is that clear. But the thing is this is not clearly eradicating our sub lemma, sub calculation, we have to use that somewhere. So that will come as a nesting. So inside this deduction theorem there can be another deduction theorem, okay. So we will write this as 1, this as 1, and again inside this we will write deduction theorem begins, but it is the second loop and then it should end somewhere else inside that loop itself. If it crosses the loop then it is wrong, it is a wrong use, because by that you have assumed both x and the other one, right, that is not permissible. So that means we can have loops like this, a nesting of structures of DTB, DTE, we can number them. Similarly this also, and when both are involved there should not be again any crisscross, that should be a nesting of this inside that, or that nesting should be inside completely this, right. Is the plan clear? So such a thing which is written in this fashion where deduction theorem, reduction ad absurdum both are included is called an informal proof. It is not very formal, because to make it formal we have to give some meta arguments, okay. We will call it an informal proof. Let us try the fifth one to illustrate how this informal proof proceeds, because we know already how it is going, it will just go the same way, but now deduction theorem, reduction ad absurdum will be used inside, okay. So we start with the original, not with this form. So we start with P implies not Q, and R implies S, not T implies Q, S implies not U, T implies not V, not U implies W. This entails P and R implies not of W implies V, okay. So what is our plan? To use deduction theorem. So we start with P and R as the extra premise, just look at that proof, you can understand how this proceeds. So we will have 3 columns now in an informal proof. First one we will give the line numbers so that we can refer them back, right. Second one we will have the correct proof, third one we will have the documentation just like our this MP, P, MT and so on. So we will be starting with P and R, its justification is extra premise which is deduction theorem begins, okay. So second line is from P and R we are using P implies not Q as a premise, so we can just add it again P and R and P implies not Q, justification is it is a premise, okay. Or there is another version, you have already P and R, so why to write it? Earlier we are writing it because entailment equivalence it is there, since it is there, it is already there as a premise, so we simply add P implies not Q, say that it is a premise, then use both the lines, okay. So we say P implies not Q, fine. Now third line from P and R, P implies not Q, we wanted to conclude not Q by modus ponens, but we cannot as it is, it has to be P. So let us write P, P and R implies P, right, it entails P, elimination, so it is 1 elimination, right. Then fourth one is from 2 and 3 we apply modus ponens to get not q. So, we document 2, 3 and modus ponens. Okay. Then fifth one will be another premise you are using, R is already there anyway, whenever you need we will bring from 1. With not q you wanted not t implies q, so introduce not t implies q premise, and then sixth one is not t, 4, 5 modus tollens. Now you see how it goes. So take it as an exercise and complete it.